Modern data transmission relies entirely on continuous physical infrastructure. When a crucial connection drops, all communication stops instantly. Within a local area network, isolating that drop is straightforward. The hardware is localized to a single building or campus, and the connections are typically direct, physical switch ports. Look at this network topology. To connect distant endpoints, a wide area network requires a packet to successfully traverse multiple distant network boundaries, moving from a local switch, through local and regional routers, across an ISP backbone, and down to a remote destination. Suppose a hard failure occurs deep in this architecture, a severed link between the remote router and the remote destination switch. A technician attempting to test connectivity from the source PC will simply receive a continuous string of request-timed-out messages on their terminal. This output confirms the failure is real. But it entirely fails to identify the location of the break. The packet could be dropping at the local gateway, inside the ISP hub, or at the remote site. Simple reachability tests are insufficient for complex diagnostics. Network engineers must deploy specialized Layer 3 tools to expose the routing path and isolate the exact point of failure. Ping is the primary administration utility used to establish a performance baseline and verify basic Layer 3 reachability between two IP addresses. As detailed in this diagram, Ping relies on the Internet Control Message Protocol, or ICMP. It utilizes two specific payload types, the echo request and the echo reply. The sequence begins when the source device constructs an ICMP echo request and forwards it toward the target IP address. If the target device receives the packet, the protocol strictly dictates that it must construct a corresponding ICMP echo reply and return it to the source. Applying this to a healthy topology, we can map the initial echo request leaving PCA and hitting the local router. The request successfully navigates transit routers to reach PCC, which then returns an echo reply back across the same infrastructure. The source machine records a precise timestamp of the departure and the arrival, displaying the total round-trip time in milliseconds. It also tracks the total number of requests sent versus replies received to calculate the exact packet loss percentage. On Cisco hardware, every successful echo reply is represented sequentially by an exclamation point. A continuous string of exclamation points proves that the logical and physical path is intact, providing the engineer with a baseline for normal network latency. We can now test this utility against our specific failure scenario, where the link to the remote switch has been severed. The echo requests successfully navigate the local and ISP routers. But they hit a physical dead end at the remote router. The Cisco terminal translates this mid-transit failure into a U character, followed by a sequence of periods. The U signifies that an error protocol data unit was received by the source, explicitly stating destination unreachable. Each subsequent period indicates that the ping utility timed out while waiting for a reply that will never arrive. A Windows OS terminal interprets the exact same physical failure by displaying the explicit text, destination host unreachable. The core diagnostic limitation is now apparent. The source device knows the target is inaccessible, but it possesses zero spatial awareness. Ping treats the multi-hop internetwork as a single, opaque entity. It confirms the existence of a failure, but provides no actionable data to tell the engineer if the packet dropped at the local gateway or 3,000 miles away. To resolve Ping's spatial limitations, engineers must rely on path discovery using Traceroute. Instead of just testing the final destination, Traceroute intentionally maps the exact transit route, measuring the delay at every single hop along the path. This split-screen diagram illustrates how different operating systems execute this process. Windows utilizes ICMP messages, while Cisco and Unix systems utilize UDP datagrams. Executing a trace maps the path in real time. Hop 1 resolves to the local router. Hop 2 routes to the ISP. Hop 3 arrives at the remote router. At this coordinate, the sequence stops, generating timeout messages instead of resolving the final switch. By tracking the packets hop by hop, the utility identifies the specific hardware node where the forwarding process fails. The engineer can now ignore the local network and the ISP entirely, focusing their investigations strictly on the routing interface connecting the remote router to the local switch. Traceroute ultimately pierces the black box, transforming a vague statement of network failure into a precise, actionable coordinate. Analyzing these tools side by side clarifies their distinct roles in an incident response. Ping is built to establish reachability. It uses ICMP echo requests to confirm connection status and measure end-to-end latency. Traceroute is built for path discovery. It uses either ICMP or UDP protocols to measure transit delays and isolate failures hop by hop. Ping answers the immediate operational question: can the source reach the destination? Traceroute answers the diagnostic question: where exactly does the path break? Both utilities operate at Layer 3 of the OSI model, relying on logical IP addressing rather than physical MAC addresses to interrogate the network. Attempting to troubleshoot a routed connection without utilizing both tools leaves an engineer reliant on assumptions and guesswork. Mastering these foundational tenets allows technicians to map logical paths, isolate specific points of failure, and enforce order over complex physical topologies.